Hello students, welcome to EC366 Real-Time Operating Systems. I am Karunakara Menon, Assistant Professor in the Electronics and Communications Engineering Department at Rajagiri School of Engineering and Technology in Kakanad. In this lecture, I'll be covering topics from Module 4 of Real-Time Operating Systems. In the earlier modules, we have looked at the functions of an operating system, different types of OS architectures, multi-programming, various kinds of scheduling algorithms, and the basic concepts of a process and process states, namely running, blocked, and ready. Module 4 talks about memory management. The topics covered are as shown in the syllabus. We will discuss what's the need for memory management, the requirements for a memory management system, memory partitioning methods, fixed partitioning and dynamic partitioning, and various types of memory allocation strategies, namely first fit, best fit, and next fit. The remaining sections of this module will be covered in the next lecture. We will start by looking at what are the basic requirements of memory management. Memory partitioning, which is rarely used now, basic blocks of memory management, paging, and segmentation. Now let's look at some standard terms used in memory management. If we recollect what we learned in computer architecture, the memory hierarchy in a computer system ranges from secondary memory, which is the disk that's large and cheap, to the main memory, which is the semiconductor memory or DRAM, which is faster and more expensive. Further up in the hierarchy, we also have various levels of caches and registers. If we divide the main memory into a number of equal sized blocks and also divide the secondary memory into a large number of equal sized blocks, then we have a frame which is defined as a fixed length block of main memory. Similarly, a page which is defined as a fixed length block of data in secondary memory, that is, on the disk. We can also have a variable size block of data on secondary memory called segments. Here is a simple diagram of memory management showing secondary memory or disk divided into equal size blocks or pages, and the main memory which is divided into equal size blocks called frames. Memory management involves moving pages of data from secondary memory to frames in the main memory, and also moving a frame worth of data to a page in the secondary memory. This is called swapping. In a uni-programming system, that is when only one program is being run at a time, main memory is divided into two parts. One part of memory is for the operating system, which includes the resident monitor and kernel, and the other part of memory is for the user program currently being executed. From here, the instructions will be fetched and executed by the CPU. In a multi-programming system, the user part of the memory must be further subdivided to accommodate multiple processes. If only a few processes are in memory, then for most of the time, all the processes will be waiting for I/O and the CPU will be idle. So memory management becomes a very important part in multi-programming systems. Memory needs to be allocated to ensure a reasonable supply of ready processes to consume available processor time. Memory management involves swapping blocks of data from secondary storage to main memory, and the memory I/O is slow compared to a CPU. So the OS must cleverly time the swapping to maximize the CPU's efficiency. To satisfy the goals of multi-programming, we need an effective memory management system. Memory needs to be allocated to ensure a reasonable supply of ready processors to consume available processor time. This is the need for memory management. What are the requirements of a memory management system? Memory management should support relocation, protection, and sharing, and it should provide logical organization and physical organization of memory. The following slides will expand on these topics. In order to execute a program, it must be loaded in memory. The program may be initially loaded in memory at one location and then may get swapped to disk after some time when it becomes idle. When it is loaded back into memory again, when it is ready to be run, it may be loaded in a different location. Requiring that the program should be loaded in the same location as before will be an unnecessary limitation. So the programmer does not know where the program will be placed in memory when it is executed. It may be moved around in main memory. It must be relocatable. Memory references must be translated to the actual physical memory addresses by the memory management system. To understand the need for relocation, let's look at the figure which shows a process image or the memory image of the process. It consists of a process control block at the beginning, followed by the entry points to the program, followed by the process itself, the data area, and the stack. Assume that the process image occupies a contiguous region of main memory. The OS needs to know the location of the process control information, the execution stack, the entry point to begin execution of the program for this process. The operating system knows this information because it is managing memory and is responsible for bringing the process into main memory. However, the processor must deal with memory references within the program, such as the branch instruction contains an address to reference the instruction to be executed next. Data reference instructions contain the address of the byte or word of data referenced. Somehow, the processor hardware and operating system software must be able to translate the memory references found in the code of the program into actual physical memory addresses, reflecting the current location of the program in main memory. Normally, a user process cannot access any portion of the operating system, neither program nor data. Usually, a program in one process cannot branch to an instruction in another process or access the data area of another process. The processor must be able to abort such instructions at the point of execution. Note that the memory protection requirement must be satisfied by the processor, that's the hardware, rather than the operating system, which is the software, because the OS cannot anticipate all the memory references that a program will make. It's only possible to check the permissibility of a memory reference at the time of execution. What are the requirements for sharing? Any protection mechanism must have the flexibility to allow several processes to access the same portion of main memory. Processes that are cooperating on some task may need to share access to the same data structure. It's better to allow each process access to the same copy of the program rather than have their own separate copy. The requirements for logical organization. Main memory is usually organized as a linear or one-dimensional address space consisting of a sequence of bytes or words. Secondary memory at its physical level is similarly organized. This does not correspond to the way in which programs are typically constructed. Most programs are organized into modules. If the operating system and compiler hardware can effectively deal with user programs and data in the form of modules of some sort, then a number of advantages can be realized. So programs are written in modules, modules can be written and compiled independently, so we need different degrees of protection to give to modules, read only or execute only, and we should be able to share modules among processes. The requirements for physical organization. We cannot leave the programmer with responsibility to manage memory. Memory available for a program plus its data may be insufficient. The programmer does not know how much space will be available. Because of this, it's clear that the task of moving information between the two levels of memory should be a system responsibility. This task is the essence of memory management. Having discussed what are the requirements for memory management, let's look at one of the early methods of memory management, partitioning. So it's one of the early methods. It was used before virtual memory came into being, and it's not much used now, but it will clarify the following discussions of virtual memory if we first look at partitioning. Virtual memory has evolved from the partitioning methods. There are many types of partitioning or various approaches to partitioning. Fixed partitioning, dynamic partitioning, simple paging, simple segmentation, virtual memory paging, virtual memory segmentation. We will be studying fixed partitioning and dynamic partitioning. The figure shows the main memory divided into partitions of 8 megabytes each. The OS is given a partition of its own of 8 megabytes. These are equal size partitions. Any process whose size is less than or equal to the partition size can be loaded into an available partition. The operating system can swap a process out of a partition if none of them are in a ready or running state. What are the issues with using fixed partitioning? A program may not fit a partition. The programmer must then design the program using overlays, which would make it more complicated. The main memory use is inefficient. Any program, no matter how small, occupies an entire partition. This results in internal fragmentation. Any remaining free space within a partition is unusable, so it creates a hole in the memory space. This is called internal fragmentation, as the unusable portion of memory is internal to its partition. The problems of equal size partitioning were: 1. The process may not fit into a partition, and 2. Internal fragmentation or unused space within the partition. Using unequal size partitions solves both the problems to an extent, but not completely. The figure shows unequal partitioning of main memory. The main memory is divided into unequal size partitions ranging from a maximum of 16 megabytes all the way down to 2 megabytes, and the OS is assigned its own block of 8 megabytes. Programs up to 16 megabytes can be accommodated without overlay. Smaller programs can be placed in smaller partitions, reducing internal fragmentation. The amount of unused space when we assign a small program is less because the partition itself is small when compared to the equal size partitions. We will take a look at what are the possible placement algorithms for fixed partitioning. In the case of equal size partitioning, we have no options and any program will be assigned to any block of a fixed equal size. That is, the placement problem is trivial. In the case of unequal partitions, we can assign each process to the smallest partition within which it will fit. So we would need a queue for each partition, and processes can be assigned in such a way as to minimize wasted memory within a partition. The figure shows two options for assigning processes in unequal sized partitions. In the figure on the left, we have separate queues for each partition. In the figure on the right, we have a single central queue from which processes can be assigned to any partition. The remaining problems with fixed partitions. The number of active processes is limited by the system. That is, it is limited by the predetermined number of partitions that were created in main memory. Another problem is that a large number of very small processes will not use the space efficiently. This is because each small process will create a large size fragment inside the partition. Because of these problems, fixed size partitioning is almost unknown today. A better partitioning method is dynamic partitioning. Here, the partitions are of variable length and number, and the process is allocated exactly as much memory as required. Let us go through an example of how dynamic partitioning works. Imagine a system with 64 megabytes of RAM. Initially, the main memory is empty, except for the operating system, which occupies 8 megabytes. Three processes are loaded in: P1, P2, and P3, leaving a hole too small for any further processes, or an empty space of 4 megabytes. At some point, none of the processes in main memory is ready. The operating system swaps out process 2, which leaves sufficient room to load a new process, process 4, but that creates another hole, an empty space of 6 megabytes. Later, a point is reached at which none of the processes in main memory is ready, but process 2 in the ready suspend state is available. Because there is insufficient room in memory for process 2, the operating system swaps out process 1 and swaps process 2 back in, leaving yet another hole or an empty space of 6 megabytes. We can see the fragments that are created are outside the partitions. This is called external fragmentation. The main memory system in the OS will perform a procedure called compaction to remove the effects of fragmentation. It will move the processes around and reorganize the memory so that the fragments can be combined to form a larger block, which can then be made into a partition and allocated to a process. Compaction implies the capability of dynamic relocation during memory management. In dynamic partitioning, the OS must decide which free block to allocate to a process. Let us look at the various types of memory allocation strategies, starting with the best fit algorithm. In this algorithm, the OS chooses the block that is closest in size to the request. This is the worst performer of the four algorithms because it is the slowest. Since the smallest block is found for a process, the smallest amount of fragmentation is left. Memory compaction must be done more often. The next algorithm for dynamic partitioning is First fit algorithm. This algorithm scans memory from the beginning and chooses the block that is large enough to fit the process. It is the fastest among the four algorithms. It may have many processes loaded in the front end of memory that must be searched over when trying to find a free block. The third algorithm for dynamic partitioning is the next fit algorithm. This scans the memory from the location of the last placement. More often allocates a block of memory at the end of memory where the largest block is found. The largest block of memory is broken up into smaller blocks. Compaction is required to obtain a large block at the end of memory. Let us compare the operation of three allocation algorithms using an example. The figure on the left shows the memory space after some allocations and swapping operations. The blocks in gray are the blocks which have been allocated so far. The blocks in white are the free blocks which may be allocated next. The last block that was used was a 22 megabyte block from which a 14 megabyte partition was created. Now, a new process of 16 megabytes, shown as the white box on the left, comes in, which needs to be allocated next. The figure on the right shows the difference between the best fit, first fit, and next fit placement algorithms in satisfying the 16 megabyte allocation request. The blocks shown in blue are the possible locations which may be assigned to the incoming 16 megabyte process. Best fit will search the entire list of available blocks and makes use of the 18 megabyte block, leaving a 2 megabyte fragment. First fit scans from the beginning of memory and allocates space in the first block which is large enough, a 22 megabyte block, resulting in a 6 megabyte fragment, and next fit scans the memory from the location that was used for the last allocation and finds the unused space at the end, resulting in a 20 megabyte fragment. In conclusion, in this video lecture, we have covered the first part of Module 4 of Real-Time Operating Systems. We discussed the need for memory management, the requirements for a memory management system, memory partitioning methods, fixed partitioning of equal and unequal size, and the issues with each of these methods. Then we looked at dynamic partitioning and various types of memory allocation strategies, namely first fit, best fit, and next fit. The remaining sections of this module will be covered in the next lecture. Thank you for attending this video lecture.